So last time we started looking at contraction analysis, and we said that Lyapunov theory was based on the idea of virtual physics, but most of the ways it was used was really virtual mechanics, virtual kinetic energy, potential energy, and so on, sums of squares. And we said it was a natural question to consider whether the same philosophy could be used as virtual fluids, and what would it give. And so we gave a number of very simple results. We said, in particular, if you have a scalar system, and if you wonder whether it is true or not that any two trajectories converge exponentially, converge exponentially to each other, right? Tend exponentially to each other. We said this was true if the derivative of f with respect to x was less than some constant negative number. And we said, so it said that if we take two trajectories, one starting with an initial condition here and one starting with an initial condition there, so x1 of t, x2 of t, this is the time axis, then they would tend to each other bounded by some kind of decreasing exponential. We also said that if we define, quote, stability in these terms, then the style of proof might be a little different from what we used to. Doesn't have to be, but it says we don't necessarily need to look at error signals. Okay? If we want to show that all trajectories of a system tend toward the desired trajectory, we can show first that the system verifies this, if that's true, right? And then we'll say the system is contracting. Any two trajectories converge to each other exponentially. And then to show that the desired behavior is also a particular trajectory of this contracting system. And since any two trajectories of this contracting system tend towards the same behavior, it means that any trajectory will tend towards the desired behavior. Okay? Similarly, if you have an observer and you make sure it's a contracting observer, then any two of its trajectories will tend towards the same things. If you also make sure that the real state is a particular trajectory of the observer, then the estimated state will tend towards the real state. And we actually said, apart from being a kind of different perspective on stability, one more inspired, if you want, by differential geometry. It had also, we also said it was particularly suitable to consider for things like designing observers, or also looking at some synchronization problems. And we gave two very, very simple examples last time. One was an observer for a second-order scalar system, in that case a van der Pol, where we measured position and wanted to get velocity, and we said basically it gives you an exact observer which exploits the nonlinear dynamics to do this. And then we also gave an example of synchronization, this example of quorum sensing of groups of system getting to some synchronized behavior as you increase the number of these systems. And we said there we could also prove that result using some this scalar property here by introducing an extra idea, which was the idea of a virtual system. Okay. Any questions so far on that? Okay, so this was kind of introductory material, all scalar, okay, but still contains some of the key ideas. Okay. All right. So the next question is, how do we get to the multidimensional case? So because this is all scalar, right? And we say, well, okay, so talking about virtual fluids. So there's lots of very simple, well, there's lots of very complicated ones, but there's also lots of very simple things you can say about fluids, okay, under certain assumption. And one of them is what's called Gauss theorem, which is a purely geometric result, which says that if you have an n-dimensional system, right, which you can view as an n-dimensional fluid if you want, right? Gauss theorem is saying if you take any volume, any region if you want, in this system, and you compute the time derivative of the volume, okay, of that region as time goes on, that time derivative is equal to the integral over that volume of the divergence of x dot. Okay. Remember, this has to do with the fact that this integral, the divergence itself, is itself equal to the flow through the boundaries of the volume. Okay, and since this is the flow of x dot, it means the change in volume. It means the change in volume, right? And so, and this divergence of x dot, of course, is df1 over dx1 plus df2 over dx2, so on, plus dfn over dxn over that same volume. Right? It's a purely geometric property. It has to do with basically the flow of x dot at the boundary, which happens to be equal to the integral of the divergence of x dot. And so you have this kind of very general property. Now, notice, of course, that suppose that we say that this divergence of x dot term, right, is for some reason less than some negative constant minus lambda, right? Then what can we say? Suppose I give you the system, you compute the divergence. What's the relation between the divergence and the Jacobian, by the way? It's just a diagonal, right? It's just a trace, right? The divergence is the trace of the Jacobian, right? It's this, right? So it's the trace of the Jacobian. So suppose that this divergence, the trace of the Jacobian, happens to always be less than some negative number, then what? So if this is true, it means that v dot, right, the derivative of the volume plus lambda v is negative, right? Which means, of course, since the volume is positive, it means that v will be less than whatever it was initially, e to the minus lambda t, and also lower bounded by 0, okay? And so it will mean that the volume tends to 0 exponentially. With rate lambda. Okay, so suppose you have this system, you compute the Jacobian everywhere, right? You compute the trace of this Jacobian. Actually, you just compute directly the trace, of course. There's no point computing the whole Jacobian if you just need the trace. So you compute the trace of this Jacobian. You suppose that this trace is always negative. It means that any volume in this state space shrinks exponentially as time goes on, and it shrinks to 0. All right? So if you think of it as a very powerful result, which is entirely contained in Gauss' theorem, right? It says if you take the divergence of the dynamics, okay, this is for a non-autonomous system, right? And that divergence is always negative, then any volume shrinks to 0. So we might say, well, actually, isn't it just what we need to extend our initial condition, df over dx less than minus lambda, to the multidimensional case, okay? Suppose we have a system whose divergence is always negative. Suppose we also know that the desired trajectory is a particular solution of its dynamics. Is it true that any point tends towards the desired trajectory? So here, of course, the subtlety, we say that the volume tends to 0, but that's not quite enough, right? Because the volume could tend to 0 and tend to, let's say, a surface, right? The volume would still be 0. What we really want to extend the scalar case up there to the multidimensional case is that any region tends to a point, to a time-varying point. Volume 0 is not enough, right? Volume 0 just means you tend towards an n-1 dimensional thing, right? Okay? So it's still something interesting to know and to remark, right? If the divergence is negative, then any volume disappears, right, exponentially. But to extend the scalar case here to the multidimensional case, we need something more specific than that. We really want to show that any volume tends to a point. Okay? Which is more precise than saying that, any volumes tends to 0. Okay. So we're going to show this multidimensional extension, or first a basic version of this multidimensional extension. We're going to show it in 3 ways, okay? It's not two, because actually the 3 ways will be useful later on in some other calculations. Okay. But we'll see the third way is the one that is going to allow us to give the most insight and to extend to a more general case. Okay. So how did we prove the result way up there on the scalar system? If we had a scalar system, we looked at d over dt of x2 minus x1 squared, right? And we computed that in terms of df over dx, and we showed that result up there. Okay? So of course, if we take the multidimensional system, right, we can do the same thing if we want, or at least try to do the same thing. Okay, so in other words, what we're going to compute is d over dt of x2 minus x1 transpose x2 minus x1 for 2 trajectories, x1 of t and x2 of t of this system. Okay, so this is the obvious multidimensional equivalent of x2 minus x1 squared. Okay, so product of 2 terms, right? So derivative of this times that plus this times the derivative, and of course the 2 terms are equal. So we can just write this as 2x2 minus x1 transpose times x2 dot minus x1 dot, which is the same as 2x2 minus x1 transpose times f of x2 t minus f of x1 and t. Okay, everybody follows that? All right. Now, this f of x2 t minus f of x1 and t. Remember when we did the proof of the scalar case, we said we could use the finite difference theorem, saying that this difference of f2 minus f1 was equal to the derivative somewhere between x1 and x2 times x2 minus x1, or we could also use an integral. Okay, so here let's try to use an integral. So the idea is we have these 2 points, x2 and x1. Okay, everything is time varying, including these 2 points. Okay, and at a given instant, we're looking at this line segment between x1 and x2. Okay, this line segment can be written in the form x1 plus lambda x2 minus x1, where lambda varies between 0 here and 1 here. Okay, and in general, you have just lambda. Okay, so everybody sees this line segment can be written x1 plus lambda times x2 minus x1, where lambda varies between 0 and 1. Okay, it's like a cursor. Okay, it's like a dial in the stereo system. Okay, you dial from x1 to x2. Okay, so if we do this, we can say, why introduce this lambda? Because this lambda is a scalar, right? And so if we do this, we can say that f of x2 minus f of x1 is the sum of all variations of f as we move just along this segment. Okay, we could compute it other ways, okay, but one way to compute them is just compute along this segment, because f is a function of x and t, right? So we do this computation at any instant. Okay, so this integral from lambda equals 0 to lambda equals 1 of d over d lambda of f of x, right, and f of x1 plus lambda x2 minus x1 d lambda. Okay. So now this quantity, we can just use the same rule, the chain rule, to write it d over dx of x1 plus lambda x2 minus x1 times d of this thing x1 plus lambda x2 minus x1 over d lambda. So this is still the same quantity, right? And this same quantity, of course, is simply d over dx of f of x1 plus lambda x2 minus x1 times x2 minus x1, right? d over d lambda of this is just x2 minus x1. So we can get it out of the integral, and we get it here. Okay, everybody follows that, right? So f1 minus f2, one way of computing it is to compute it by the just along this line, right? It's one way of computing it. If we do that, it means we just compute it for all the variations along this line as lambda varies. Using the chain rule, d over d lambda is d over dx, d over dx over d lambda, right? This is the same, and dx over d lambda is simply x2 minus x1, which is independent of lambda. Okay, so we get it out of the integral. Okay. So if we use this relation here, okay, we see that d over dt of x2 minus x1 transpose x2 minus x1 is equal to 2 x2 minus x1 transpose times this, and therefore is equal to this integral from lambda equals 0 to lambda equal 1 of d over dx of f of x1 plus lambda x2 minus x1 d lambda. It takes longer to write than to understand it, right? Because it's just has all these indices, but it's not a big deal. So we just get this. Okay. And so if we assume that this Jacobian df over dx is always less than some minus alpha times I, with alpha a positive constant, then this will be less than minus alpha x2 minus x1 transpose x2 minus x1. Right, because we're integrating this quantity, which is always less than minus alpha I, between 0 and 1. Okay. And we see, therefore, that x2 minus x1 transpose x2 minus x1, right? So this quantity tends to 0 exponentially with rate 2 lambda, okay, because there was a 2, by the way, floating around. 2 alpha, sorry. We have a 2 here, which I've put here, which means, of course, that x2 minus x1, the square root of that, tends to 0 with rate alpha. Okay? So what have we just shown? I'll invite you to read this, but it looks complicated, but it's really just, it's just because we play with different variables, but it's very simple. Right? The only idea is this, right, is that you pick a particular path and you parameterize it with a scalar. So you have this result. And so this result says that if df over dx is less than minus alpha I, in other words, if the Jacobian of the system is uniformly negative definite, okay, so if for some constant alpha positive for any x for any t, df over dx less than minus alpha I, i.e. df over dx is uniformly negative definite, okay, uniformly in state and time, i.e. all eigenvalues of the symmetric part 1/2 of df over dx plus df over dx transpose are uniformly strictly negative. Remember, when we say this for a matrix, right, is equivalent of saying this for the symmetric part, okay? Because remember the fact that the matrix is positive definite or not only depends on the symmetric part, because it depends only on the quadratic form x transpose mx, right, as we saw. So if the Jacobian is uniformly negative definite, meaning this, which says if the eigenvalues of the symmetric part of the Jacobian are all strictly negative, okay, then all trajectories converge to each other exponentially with rate alpha. Okay? So that's the exact equivalent of this this scalar result here in the, well, exact version, if you want, of the scalar result here in the vector case. Which is that if the Jacobian is uniformly negative definite, then any two trajectories tend to each other exponentially. Remember when we talked about linear time-varying system, we gave a condition for linear time-varying systems to tend to 0, right, which was very similar to this. They're saying symmetric part of df over dx. Okay, so let's just give a little example. So, as you all know, Edward Lorenz was a professor here at MIT who recently lived at the 100 Memorial Drive, is the founder, and who died a couple of years ago, is the founder of what's called the theory of chaos. And the idea of chaos is that if you have a nonlinear system which has local instabilities, okay, so if you take two trajectories which are very near each other, if you look at where they are later, they could be quite far apart. Okay, so if you have local instabilities, then of course it's very hard to predict the behavior of these systems. All right, because if you make a small mistake in your measurement or your estimate of where you are, then basically you've jumped to the next trajectory, and so a little while later you're far away from where you thought where you should be. Okay? So if you have local instabilities, then of course it's hard to do prediction. Okay? And so Lorenz wrote a paper in 1963, which was called Deterministic Non-Periodic Flow. It was a nice technical title, and almost nobody paid attention. Yeah. So he said that, okay, and he wrote this model, which is now called the Lorenz attractor, based on the simplification of Navier-Stokes equation. And you know, if you look at the citations until after 1963, almost nobody paid attention. So in 1972, at the instigation of a friend, he decided to talk about the same idea, of course, which by then had expanded too, but give it a more sexy title. Okay, and so the more sexy title was predictability: does the flap of a butterfly wing in Brazil set off a tornado in Texas? Okay, which was much better, of course, than deterministic non-periodic flow, right? And so this gave rise to the term the butterfly effect, right? Which is this notion of, a very small change can have huge consequences because you have local instabilities, okay? So in principle, at least based on these models, the flap of butterfly wings, in Brazil could set off tornadoes in Texas, okay? At least, as a reflection of this model, okay? So the butterfly effect, okay? And so if you look at the citations, then they picked up, violently. And of course, this paper now is one of the most cited ever, okay? But it wasn't for 9 years. Okay, so So why am I talking to you about the Lorentz system? So let me give you the Lorentz system, which again is a simplification. It's based on a simplified model of Navier-Stokes equation and Bénard convection. So this form. Okay, so 3 variable x, y, z. 3 positive constants, strictly positive constants, sigma, rho, and beta. Okay, and that's the model. Now, this model, by the way, apart from creating this whole field of chaos, gave rise much later on to a whole literature on how to possibly make secure communications using these kinds of dynamics. And a simplified version of that is the following. Suppose that we have this system. Okay. So it's a nonlinear system. Now remember well, yes. Okay, hopefully. Now remember we said we call a system contracting if any 2 trajectories converge to each other exponentially. Okay. So based on what I told you, is the system contracting? Not at all, right? Actually, it's more like the opposite of contracting, right? When it tends toward its retractor, it's actually extremely sensitive to initial conditions, right? So this system is not contracting at all. Okay, it's a system with local, strong local instabilities and so on. So, okay. Now, however, suppose that you're given this system, and you're given a measurement of x, let's say a reasonably precise measurement of x. And you're told, could you build an observer of this system? Okay, so you measure x, measurement of x. And you asked to build an observer for the system. In other words, something that will do a good job at following what this chaotic system does. Okay? Now, suppose you're very lazy or in a hurry or you want to move to the next thing, okay? You have the idea of saying, well, sitting on my computer, let me just try to copy the second and third equations, put y hat and z hat, okay? And use the measurement x and see what happens, right? It sounds optimistic, but why not, right? So suppose you build this observer obtained by just taking the last 2 equations. You measure x, you want estimates of y and z. Okay, so you put y hat and z hat, and you keep x. Right, so that's y hat dot is equal to rho x minus y hat minus xz hat. And z hat dot is equal to minus beta z hat plus xy hat. All right? So suppose this is your observer, okay? So it's a reduced order observer, but of course, you can call this an observer, but to show it's really an observer, you have to show that indeed it will work. Okay. Okay. So suppose we try to show that indeed it works. Okay, so we have this system. We measure x, and we try to estimate y and z. So we estimate y hat and z hat, which hopefully tend towards y and z. All right. How would we show, based on what we just said, that this works? Well, one way would be to try to show that this dynamics is contracting. Okay, so that any two solutions tend toward the same thing. Okay. And two, to show that the real thing is a particular trajectory of this. Okay. Which one is trivial? Well, the second one, right? The real thing is obviously a particular trajectory of this because you were so lazy you just copied the system. Right? So obviously the real YZ are a particular solution of this. Okay? So okay? So that's obvious. Now, that's very simple. Now, how do we show that it's contracting? Well, we could try to use this result. Okay, so we could say theorem, right? We could try to use this result. And so what is the Jacobian of this system? By the way, I'll give you a couple of notes on this, right? So what is df over dx? Okay, so the Jacobian. So in other words, d of y hat dot z hat dot over y hat z hat. Can somebody tell me? So for this system, right, it's like the observer we did when we looked at the van der Pol, we measured position and we wanted velocity, right? For this system, x is an external variable, it's a function of time, right? Right? So when we compute the Jacobian, what do we get? Can you tell me? So -1 and minus x plus x minus beta. Right? That's the Jacobian. Is that clear? Right? Because x, of course, is this external variable. For this system, it's just x of t, right? So it's just a function of time. Right? So, what about the symmetric part? The symmetric part of this Jacobian, what is this equal to? Well, we see that pleasantly this x and minus x, which were, okay, the only thing which were making it a little difficult, disappear. It's not entirely surprising because after all it came from the Navier-Stokes equations and so on. Okay, so the symmetric part is just this, right? And therefore, it is negative definite, right? And remember we said that beta, sigma, and rho were all positive constant, right? So it's less actually than minus the minimum of 1 and beta times identity, right? Which is, of course, a positive number. Right, it's a diagonal matrix, right? So its eigenvalues are 1 and minus 1 minus beta, right? So it's less than whatever of these two is smallest in absolute value times identity. So what's the result of this, right? The result of this is that if you take this system, build this trivial observer obtained by just copying the system and using the actual x, you can show in one line that this observer globally exponentially converges to the real y and z. starting from any initial condition on y and z, although the system is chaotic, unstable, and all these weird things, right? The y hat and z hat are going to converge to y and z exponentially fast, and you know the rate, right? The rate is the minimum of 1 and beta. Right? And we'll show a little later, but you can already guess this, right? This is exponential convergence, so it's actually quite robust. You could show that, for instance, if this was this system plus a bounded disturbance, so it would seem that you have this unstable system plus this bounded disturbance, it's all going to be messy, right? But no, actually you can show that if there's a bounded disturbance, actually, it will just give a bounded error to this observer. Okay? So although the system itself is wildly unstable, it's actually the poster system for instability, right? You can build globally exponentially convergent observer, which is actually also robust. Okay. And noticed here, it's also an example of why we said you don't necessarily need to use error signals. We didn't use error signals. We didn't use y hat minus y, right? We just directly did this. Okay. Questions about that? Questions? Okay. So now we have a third very simple example, if you want, of application of these ideas. Questions? Okay. So, all right. So, now, very briefly, just because it's something that technically will be useful a little later, we can give a second proof of this theorem. So more or less the same idea, but a little differently. Okay, it's more so that you can think of the implications. So here, we looked at an integral, okay? But in a sense, what we care about, right, is to compute x2 minus 1 transpose f of x1t minus f of x2t, right? So here we computed it using an integral. But we can also do something a little differently, okay? Notice that, so let's place ourselves at a given time. We have a given x1 and x2. We're just doing algebra, okay? Time is given, x2 and x1 are given. We're just doing algebra, okay? So we can say that x2 minus x1 transpose f of x, of course, is a scalar. Right, so far it's clear. And to this scalar, we can apply the finite difference theorem directly by using, again, this parametrization by lambda. Okay, so in other words, this quantity here, x2 minus x1 transpose f, sorry, it was f of x2 minus f of x1. F of x2t minus f of x1t, we can rewrite as x2 minus x1, that's a given here, f of x1 plus lambda x2 minus x1 for lambda equal 1 minus f, again it's harder to write than just to think about, okay, lambda x2 minus x1 for lambda equals 0. So, in other words, we're writing this thing as x transpose x2 minus x1 transpose times this, and this x2 is x1 plus lambda x2 minus x1 for lambda equal 1, and x1 is same quantity for lambda equals 0. Okay. Now, why am I doing this? Okay, because now we have a scalar which depends on another scalar lambda, so we can apply the finite difference theorem to it. All right? Now we have this scalar which depends just on another scalar lambda which varies between 0 and 1, so we can apply the finite difference theorem to it, okay? And so it will say that this quantity is equal to x2 minus x1 transpose times df over d lambda computed as at some lambda question mark between 0 and 1, okay, times 1 minus 0, because lambda equal 1 minus lambda equals 0. And then, of course, with df over lambda, we can compute as d over dx plus times dx over lambda as before. So it's x2 minus x1 transpose df over dx at x1 plus lambda x2 minus x1 question mark times x2 minus x1. Okay. So it's just another way to prove the same result. Okay, you see then that, again, if this Jacobian is uniformly negative definite, then you can do the same thing, right? This will be less than minus 2 alpha x2 minus x1 transpose x2 minus x1. Okay. The difference is that instead of computing an integral, we just said this is a scalar. Instead of computing f2 minus f1 first and then multiplying, we compute this directly. We say it's a scalar, it depends on the scalar. So we can apply the finite difference theorem very easily to it. And it will involve some value lambda question mark between 0 and 1. And so the algebra will say it's equal to this times the Jacobian at that value of lambda, which we don't know, times x2 minus x1. And since we assume the Jacobian is negative definite everywhere, we get the same result, but we don't use an integral. Okay? And I'm saying this because it's a technical result which will be useful later. Okay? So it's a slightly different point of view. Instead of computing f2 minus f1 with an integral and then multiplying, we compute directly the scalar as a function of the scalar lambda. Okay? All right. Now, we're going to do the third proof, and that's going to be the real one. Okay, so that's going to be the one we're going to be interested in because that's the one that is going to generalize easily and is kind of the essence of the story. Okay, so for this, I want to introduce a notation which is delta x, which is the same delta x that you see in fluids and also in optimal control, okay? So it's called a virtual displacement. And what it means is that it's a differential variation at fixed time. So in other words, instead of looking at two trajectories starting from two initial conditions arbitrarily far and looking at what they're doing, we're going to look at two trajectories infinitely close, okay, at some instant, okay? And we're just going to look at the variation between x1 and x2, okay, at a given time. Okay, so it's dx, right? So it's a differential, but it's a differential at fixed time. Okay, so you take a picture at time t, and you have x1 and x1 plus delta x. Right. You have x1, and x2 is simply x1 plus delta x, right? At given time t. All right. Now, you can do computations on these virtual displacements. And actually, there's a whole theoretical background to do this. But if you think of it, right, when we write that d of sine theta is equal to cosine theta d theta, right? It's an exact relation between differentials. Okay, it's also a way to linearize sine theta, right? But it's also an exact relation between differential. D of sine theta is equal to cosine theta d theta. So here, same kind of general idea. We're going to play with exact relations on differentials. So suppose we compute d over dt of delta x. Okay, I could do this a little more formally, but what is that going to be equal to? Well, it's going to be the equivalent of f2 minus f1, right? But here we're just going in at a point x between x and x plus delta x. So we simply have the Jacobian itself, right, times delta x. Right? It's the integral of the Jacobian between x1 and x1 plus delta x. So it's simply the Jacobian times delta x. Okay? All right. Now, being a little bolder, and again, you know, this can be formalized a little, but it's fairly straightforward conceptually. We can look at the time derivative of the length, if you want, of this differential element, right? And again, it's the product of two vectors, right? And so we get two terms, both of which are equal. Okay, so we get 2 times delta x d over dt of delta x. And we just said that d over dt of delta x was equal to Jacobian times delta x. All right? It's basically a very usual calculation, except we do it on differentials. Okay? Now, assume again, remember this is the third proof, right? So assume again that this condition is true. Okay. So it says then this is going to be less than minus 2 alpha times delta x transpose delta x, which will of course imply that delta x tends to 0 exponentially with rate alpha. Since delta x squared tends to 0 exponentially with rate 2 alpha. Okay, so here we use again the same assumption, okay? For some constant positive alpha. Okay? So we see that if we make this assumption, then any small variation between two trajectories will disappear. Okay? In a sense, we're doing the linearization of the system, but the linearization everywhere. Okay? Not around a point, but everywhere. Okay? We're computing a Jacobian everywhere. Okay? And we're saying if this Jacobian is uniformly negative definite, we're not saying, we know that's wrong actually. We're not saying if the Jacobian has its eigenvalues in the left half plane or whatever. We're saying if the Jacobian is uniformly negative definite, then any small variation will disappear. Okay. You might say, well, you know, that's nice to say any small variation will disappear, but what about big variation? Okay, so let's do that. So let's compute x1 and x2 starting from big variation, not small ones like that. And here you can see in a sense that why I said it's kind of a differential Lyapunov framework. In a sense, it's Riemann coming to the rescue of Lyapunov. Okay, so let me explain. So suppose you have two initial conditions of the system, and we're just looking at the flow, okay, as time goes on. So at time t equals 0, you're here. And suppose you draw a line between the two, okay, a line segment. Okay, so this is the line segment between the two, and it's at time t equals 0. So think of it, you know, it's like a river, you know, and you put in lots of little buoys on a straight line at the river at time t equals 0, and you let it go. Lots of little floats. Okay, so you're putting these little floats on a straight line at time t equals 0, and you let it go. Okay, or you're putting some dye or something like that. Okay. So now you look at where you are later on at some time t, okay? So, of course, at some time t later on, this is not a line segment anymore, right? All these little floats have gone their merry way, right? So you might have something like this, okay? So this is where this line segment has what this line segment has transformed to at this time t equal t. Okay? Now, suppose that this condition is verified. Well, we know that if we take all the small variations between these little floats, right, a la Riemann, right, then we know that we're going to get in there the same ones, right? But each of them will have shrunk exponentially, right? So what can we say? We can say that at time t equals t, of course, we can do the exact same thing by taking an integral and the derivative of this integral, right? I'm just giving it to you graphically. So what can we say at time t? We can say that each of these infinitesimal line segments has shrunk exponentially with a rate alpha. So the total length of this orange thing is less than the initial length e to the minus alpha t, right? Because each of these line segments has shrunk. Okay? We're doing computations on scalars here, just on lengths, right? So the total length of this orange thing is less than the initial length e to the minus alpha t. But of course, if we now do the straight line segment between where these 2 points x1 of t and x2 of t are, that line segment is of course smaller than the orange thing, so it's also less than the initial value e to the minus lambda t, right? So if you have this differential condition, that the Jacobian is uniformly negative definite everywhere, then it will be true that the distance between any two trajectories tends to 0 exponentially, as of course we've already proved in two different ways. Okay? But that's because this one is going to be something which can extend nicely. All right, so that's the basic idea. we do an exact differential computation, okay, and then we compute lengths. We get back to scalars, and then we get conclusion out of these scalars. Okay, so from here we can say that any differential displacement shrinks exponentially to 0, and from this reasoning, or the integral version of this reasoning, we can show what we've already shown, that the distance between any two trajectories tends exponentially to 0. Okay. All right. And so, where are we? We have several proofs of the fact that if the Jacobian is uniformly negative definite and is bounded by minus alpha I, then any two trajectories, upper bounded by minus alpha I, then any two trajectories of the system will tend towards each other with an exponential rate guaranteed to be less or equal to alpha. Okay, so that's a sufficient condition, of course. Okay, we've just said if that's true, then okay. Now, is that a necessary condition? Suppose that I was going to say, well, we're now going to show that this condition is actually necessary. Well, it can't be, right? Because if you remember, if we have a system, if we take an LTI system, x dot equal ax, right? Suppose we applied this sufficient condition to it, right? It would say that A is negative definite, okay? So in other words, the eigenvalues, symmetric part of A are all negative, all right? But we said that when we talked about Lyapunov matrix equation, how to describe linear systems with Lyapunov tools, we said in general it doesn't work to take V equal X transpose X, right? Because the V dot, which would be X transpose A plus A transpose X, if A is stable, this V dot is not necessarily negative, all right? So we said explicitly, if you have a linear stable system, it's not necessary and sufficient that the eigenvalue symmetric part of A are negative. That's why we needed, remember, the Lyapunov matrix equation, which was saying that A transpose P plus PA was equal to minus Q, which was negative definite. Okay, but we needed this P. Okay. So we have a sufficient condition, but it's clearly not necessary and sufficient because even in the case of linear time invariant system, it's clearly not necessary. Right? We can very well have strictly stable linear system where this doesn't work. That's why we need the Lyapunov matrix equation. But of course, we can start with this sufficient condition and just try to generalize it, okay, to make it more general. And perhaps if we make it very general, then we'll end up with a necessary and sufficient condition. Right? Here we said, well, we take X transpose X, not general enough, but X transpose PX is general enough, okay, if we do the right things. So what's the equivalent of X transpose PX? Well, we could say, in a sense, X transpose PX is the same as changing variables, right? P is a positive definite matrix. It can itself be written as a product, as a square, right? So it's the same as a change of variables, right? So we can say, okay, we have this sufficient condition, but the Jacobian be negative definite. Okay, so I have my system x dot equal x of x and t. Perhaps before applying this sufficient condition, I could try to make a change of variables and then apply the sufficient condition. Okay? In a sense, especially coming from feedback linearization, right? We know that there's lots of things we can do with change of variables. Okay? So we could say, well, perhaps we can define a new variable, z equals z of xt. And perhaps in terms of this new variable, if the corresponding Jacobian is negative definite, then any two trajectories will converge to each other. Okay, so we need, at a given t, we need this transformation to be smooth, invertible, the usual thing, right? So we have a new state. So that's one idea, to say, okay, we have a sufficient signature in terms of x. We could say, well, it doesn't have to be in terms of x, right? It can be in terms of any one-to-one transform variable within small technical conditions. Okay? So let's do that. So we could rewrite this as z and so on and then compute the Jacobian, but it's easier to go directly in differential forms, right? Because we're going to compute the Jacobian anyway, right? And the Jacobian is unique. So we can look at delta z, right? And delta z is dz over dx times x of t times delta x. And this matrix we're going to call theta. Right, in other words, we could take this system, replace, okay, and we would have z inverse and things like that. We can do it directly on the differential form because we care only about the Jacobian anyway. So d over dt of delta z is d over dt of theta delta x. So it's theta dot delta x plus theta d over dt of x, d over dt of delta x. D over dt of delta x, we know what that is, okay? So it's theta dot delta x plus theta Jacobian delta x. So it's theta dot plus theta Jacobian delta x. And of course, if we assume a smooth, bounded, with an inverse bounded one-to-one transformation, because we have this one-to-one transformation, there's a theta inverse, okay? And so we can rewrite the entire thing as theta df over dx, theta inverse, plus theta dot theta inverse delta z. Okay, so d over dt delta z is equal to this quantity. D over dx of df over dx multiplied by theta and theta inverse, and theta dot theta inverse. Now, this is not entirely surprising in a sense, because if theta was constant, this would just be, a usual change of variables, matrix, and it times Jacobian times its inverse, okay? And so this comes from the fact that theta is not constant. Okay. Now, this, in a sense, we can give it a name, okay? Let's call it, for instance, capital F. And it's a sort of a Jacobian, right? It's what you could call a generalized Jacobian, because we had up there, I'll rewrite it, right? We had d over dt of delta x was equal to the Jacobian times delta x, okay? And now we have d over dt of delta z is equal to this generalized Jacobian, capital F, times delta z. All right? And so if f now is uniformly negative definite, and we still need this invertibility condition, okay, so still need these to be nice and invertible, so it's easy to show that you can get this by requiring that theta transpose theta be, which is a square, of course, be positive definite, okay, so right, this is basically saying that theta is invertible, okay, but it's saying also it's uniformly invertible, right? So if f is larger than minus alpha I and this square is larger than some strictly positive definite matrix, okay, then any delta z will tend to 0 exponentially, which will imply that any delta x tends to 0 exponentially, which will imply that any x2 minus x1 tends to 0 exponentially. So if we're just saying, okay, instead of applying this basic contraction theorem to the state itself as it comes, we could apply to a one-to-one transformation of this state, and obviously it will give us a more general formulation, because we'll say, for any matrix theta that verifies this, we can do this one-to-one transformation, and if one of these, if the corresponding Jacobian is negative definite, then it will work, okay? Notice it's basically, except theta is time varying, it's basically the same idea as the Lyapunov matrix equation, right? Because if you think of it also, we could say that delta z transpose, this square length in delta z, right, is equal to delta x theta transpose theta delta x, okay? Which is kind of plays the role of P, if you want. Right, so delta z transpose delta z, since delta z is equal to this, you can write it as delta x transpose theta transpose delta x, right? And for those of you familiar with this, right, what is this called then? It's what defines a metric, right? Or metric tensor if you want. So this is saying, okay, I have my space delta x, but instead of measuring lengths as delta x square, I'm going to weigh them with a matrix which is itself a function of state and time. So it's like a Riemannian metric. Okay? So, and of course, in the linear case, this metric would simply be, linear time invariant would simply be P. All right. So that's where we are, okay? So we started with a basic theorem. We proved 3 different ways, okay? We said, well, now that we have this, we might as well make it more general in a quasi-trivial way with small technical, being careful a little technically, by just doing a change of state, one-to-one change of state, smooth change of state, okay? So that will certainly be more general. And that will certainly cover this case, okay? So at least that won't be a counterexample anymore of the fact that it's not necessary and sufficient. But we see actually this entire, here we used this fact to get this result, right? Z equals z of xt gives us this, and then we did the calculation. But you see that the calculation started here. Right? In other words, this explicitly was never used in the calculation, only this. Right? Now, why is that interesting? Because you see, immediately it can make it even more general, right? Suppose I start with delta x, and any invertible matrix verifying this, I can call that delta z, right? Delta z equals theta delta x, okay? I could call it red sun to whatever, right? I can call it delta z, right? And I can do the exact same algebra. Nothing will change. Okay. Now, why is this interesting? Well, precisely because, as we said 2 lectures ago, not any vector is a gradient. You see, if you come from here to there, then of course that's true. But in general, from here, you cannot integrate to find a z. So in other words, this form is much, much more general than this form. Right? This form is much, much more general than this form because you know, in general, if I compute theta delta x, I can call it delta z, but it doesn't mean z exists, right? I can just give it a name and call it delta z. Right? But in general, it's not integrable, right? It may not be integrable. Not any vector is a gradient. Okay. And remember, that was the key difficulty when we talked about feedback generalization. It was the second condition, the involutivity condition, right, which imposed that you had this exact gradient, right? But in a sense, in a different context here, we see that, at least at this level, this is something we don't need at all. Right? We can just see this as a differential change of coordinates, right, without an explicit z. Okay, so I know it's a subtle point, right, but you can see why it's more general. Okay, so we start with x, we continue with z of xt, and then we said forget about z of xt, let's just go directly delta z equal theta delta x. So then it's even more general. And you can show then that under certain simple conditions, it becomes so general that actually it becomes necessary and sufficient condition. Necessary and sufficient. In other words, it becomes true that it will be true that any 2 trajectories will tend to each other exponentially if and only if there exists a transformation theta of xt such that basically theta transpose theta is uniformly positive definite and the associated generalized Jacobian is uniformly negative definite. All right? So we started something which was sufficient but clearly not necessary. We made it more and more general, first by doing a change of coordinates, change of state, and then by doing something much more general than a change of state, just a differential change of state, which is just basically a notation, delta z equal theta delta x. Okay? Or picking a different metric. And by doing so, we get a result which now is very broad, which says that if there exists a transformation like this, so if there exists a metric, okay, such that the corresponding generalized Jacobian is uniformly negative definite, then any 2 trajectories of the system will tend together exponentially fast. Okay? So we'll see simple applications of this next time.